So hello learners, so in this particular lecture and session we will talk about breadth first search. We'll discuss about the algorithm and we'll discuss about more examples with the algorithm we will see. Now we've already discussed about the depth first search. Now breadth first search is based along the same lines. Depth first search is again traversing the nodes in a graph. The same will be done by the breadth first search. It will also be traversing the nodes, but the pattern here that here will be used will be different as compared to the depth first search. So in the depth first search we are all using the stack data structure, and in the breadth first search we are using the queue data structure. So the difference between the stack and queue is that in the queue data structure the element which is visited first will be out of the queue. Now in the stack data structure was that the element which is visited first will be out of the stack in the last. Okay, so this is the difference. So the color black in the depth first search will be that wherever you are not able to find any adjacent nodes. So you are seeing here that if there are five vertices, you have put first vertex, second, third, fourth, fifth. Now when you are, because first is calling second, second is calling third, third is calling fourth, and fourth is calling fifth, recursive calls. Now when you get to fifth, the fifth node will be the first to be colored as black, because every adjacent node of fifth is already being visited. Okay, so now if you're seeing here, stack data structure is arranged in such a way that the last element which came is the first one to leave, but in the breadth first search the first element which came in the queue will be the first element to leave. Now what it means is that the first element, suppose this is a queue, now the first element enters the queue, so it will be visited and it will be marked as black. Okay, so this is the difference between the depth first search and the breadth first search algorithm. Okay, so again it's a traversing mean, so you have to mark all the vertices as visited. You have to start with the vertex V. So find an unvisited vertex. So this is the procedure of breadth first search. You can look into the slide as well. So find an unvisited vertex that are adjacent to V and mark them visited. Now next consider all the adjacent nodes that is being not visited, so unvisited nodes, and then continue the process until all the nodes are being explored. Okay, so the procedure is very much similar to the depth first search, because here also we will be putting in the queue all the unvisited nodes and all the adjacent node of a particular node which is being explored. Okay, moving on further, this is the simplest explanation of an algorithm of breadth first search. Now what is a breadth first search? Breadth first search algorithm is being the argument here is being V, which is the vertex set. Now you have to visit the first vertex, so that is why it is U becomes equal to V, and you will mark that vertex, the first vertex as visited, equal to 1. Now you have to repeat this for all the vertices. How will you repeat? If the vertices is being that the vertex visited is being 0, then you will add that adjacent vertex to the queue. So here add W to Q and mark the visited as 1. So you have to visit one by one, and if Q is being empty, then you have to get out of the loop, and in the end you will delete the element from the loop or from the queue. Okay, so it's very simple explanation of an algorithm in BFS. So moving on forward, what will be the complexity here? That the loop here will be executed as many as the vertices time. So big O of V will be there. Another is that you will again add the adjacent edges adjacent vertices one by one. So the edges will all be explored so you have to add the edges part as well. And then another part is that inside while loop, that repeat loop, there is a loop which will execute at most O of E times, as it will be at most the sum of the degree of the adjacency for all vertex V in the vertex set V. Okay, so you have to do that. So in the end, the overall complexity is very similar to the DFS, which is again a big O of V vertex set plus the E, which is the edge set. Okay, so again the same example will also be discussed here, 1 2 3 4, and the adjacency list of the example is also being shown. Okay, so moving on forward, how it will work. So now first thing that you have to maintain a array which will have only two entries, which will be either 0 or 1, where 0 means that the vertices are not visited and 1 means the vertices are being visited. Okay, so here again are 5 visited. In the starting it will be 0, but in the first part you have to visit some vertex. Okay, so suppose I have visited the 1 vertex, the name of the vertex is 1, I have visited it. Now when you visit this vertex, first of all you have to add it to the queue, because you are visiting this particular, and you have to mark the visit of one vertex as 1. Okay, so you check in the slide that the vertex 1 in the table, the vertex 1 is being put as 1, it means it is being visited, and in the queue the vertex 1 is also being added. Now the next step is very simple, that you have to consider the vertex vertex 1, and you have to add the adjacent adjacent vertices to the vertex 1. Okay, so now for the vertex 1, the vertex 2 and 3 are adjacent. Now if they are adjacent, what it means is that you have to add it to the queue. So you can think of it like that, 2 and 3 is kind of a queue. You can check here in the queue, 2 and 3 is being added first. Now which particular vertex you want to visit, you can visit 2 or 3. Again there is no difference between them, the priority of both the vertex is same. You can visit 3 first as well, you can visit 2 as well. So whatever you want, you can do that here. Now when you are visiting in the next step, you will visit, suppose I am visiting the next vertex, which is 2. Now when I have visited the first vertex, which is referred to as 2, I will mark the visited of 2 as 1. So check in the red text that 2 is marked as 1 here, it means the vertex 2 is being visited, and now the u becomes 2. The u means the value becomes 2. Now the next step will be, again you have to add the adjacent vertices to 2. So what are the adjacent vertices to 2? 1, 3, 4 and 5. So check in the already built queue, 2 and 3 is already being added, so you have to add, 1 is already being visited, and you have to add only 4 and 5. Okay, so see here, whenever you have visited a particular node, after that you are just marking it as black. Okay, so it is not like recursive calling going on here. So whichever particular node visited first, which will be the function call is being closed there, so it is marked as black. Okay, so now again check in the queue which is the next node to visit. Okay, so the next node to visit is 3. Okay, so go again, you will be marked as 3 here now, and what will you do when you visit 3? First you will take the visited of 3 equal to 1, and then you will put u equal to 3, which is the vertex, and add all the corresponding or adjacent edges to 3, which is 1, 2 and 4. So already 1, 2 is being visited and finished, and you will go towards the 4. So 4 is also being, I think, yeah, 4 is also being in the queue. So there is no new vertex that is being added here. Okay, so keep that in mind. Now move on forward. Now which is the next vertex to visit? So keep that in mind. If you want to visit the next vertex, just take a look at the queue part. Okay, so in the queue, the next vertex to visit is 4. So you have visited 4, mark the visited of 4 as 1, first step. Second step is that you have to add the adjacent nodes to 4, which is what? 5. Now 5 is already being added into the queue, so there is no need to add 5 again. Okay, so now the last vertex that is left in the queue to be visited is 5. So go for it. So you will mark the visited of 5 as 1, and then you will check that you will be set as 5, and then what are the adjacent vertices to 5, which is 2 and 4. Okay, so they are already being visited and it is marked as black also. So what it means is that your queue becomes empty. So now this will be your order of breadth first search. So this is how breadth first search algorithm works. So keep that in mind. It is a different from depth first search in the form of elements entering and leaving. So in the stack form, the first element enter is the last element to leave. It means the first element will be the last one to be marked as black. But in the queue here, the first element that entered in the queue will be marked as visited and will be taken out of the queue and marked black at the same time. Okay, so now check what is the summary of breadth first search algorithm. So after exploring the vertex of a given graph by BFS algorithm, BFS traversal sequence is 1, 2, 3, 4 and 5. Again, I've already told you that adjacent nodes, like for 1, the adjacent nodes is 2 and 3. So you can go for 3 as well, because both have same priority, both are adjacent to 1. So another breadth first search traversal order can also be possible, like 1, 3, 2, 4, 5 is also possible. So this is not wrong, this is also correct. Okay, so in this algorithm, sequence of the vertex visited or explored may vary, so it is also being there. Keep that in mind. The final sequence of the vertex visited, it depends upon the adjacency list. You can think of it like that. You can look for the adjacency list, because for 1, 2 and 3 are adjacent to 1, so both of them have the same priority. Okay, so again the result, if you check here, both the results in depth first search and breadth first search are same, because the visited order, I think, will not vary, but because these are same examples, so it is not varying. But in some similar examples, the breadth first search and the depth first search can vary. Okay, keep that in mind, that it is not like in this particular example it is becoming the same order, but it is not always true. So this is not always true. Breadth first search will have a different order as well, and depth first search can have a different order as compared to breadth first search, because both of them are using a different data structure for solving. Okay, now what are the applications of breadth first search? So this is also possible for depth first search. So these are both the applications are possible in depth first search and breadth first search as well. The first one is the shortest path and the distance finding. Again, breadth first search also does not give you the shortest path always. So for always, if you want the shortest path always, you can go for Dijkastra algorithm and other algorithms. But still many times depth first search and breadth first search can result in a shortest path. Okay, so BFS can be used to find shortest path and distance between two vertices in an unweighted graph or a weighted graph. Weighted graph means that wherever on the edges, if the weight of the edge is being written, you can call it a weighted graph. By exploring the graph level by level, BFS guarantees that the first time a vertex is discovered during the traversal, the vertex is the closer to the starting vertex. Another is the application here that is being used in web crawling. So what happens in web crawling is that you just write a program for web crawler. So what it will do, it will scan throughout the web for a particular keyword. So it can simply do that. Search engines and web crawlers also use BFS to discover and index web pages. Starting from a given web page, BFS is employed to visit its linked page. The similar way that we have done that first graph node is visited, then you have to look for the another node, which depends upon the order. If you are using depth first search, the order can be different, and if you are using breadth first search, the order can be different. Okay, so most of the time breadth first search can be used to index various pages in web. Okay. Another application is social networking. So graph search is a feature that is being used in Facebook and Instagram. So when you search for a particular person, if that person lies in your friend list and in the mutual friend list or friend list of friends, it lies, it will be given a higher priority. Why? Because it is linked. So it means that first vertex becomes you and another vertices will becomes your friends. Okay, so this is how the social networking part and all the modern social networking app works and employs DFS and BFS. Another is puzzle solving. So it is also used in puzzle solving. So if you have heard about the Rubik's Cube, it is used in a 15 puzzle or Rubik Cube algorithm as well. So you can simply try a BFS algorithm, it will work. It will have a certain set of rules. If you follow it again and again, you can simply solve the Rubik's Cube. Another is that you can also find connected components. This is not only true for BFS, it is also true for DFS. So these are common applications to both the searching algorithms. Okay. So BFS can be used to find connected components in an undirected graph. By starting BFS from each unvisited vertex, we can explore and label all the vertex belonging to the same or connected component. Another is minimum spanning tree. Minimum spanning tree can also, BFS can be used to find minimum spanning tree as well. So minimum spanning tree, if you have heard about Crucial and Prim's algorithm, so they are used to build minimum spanning tree. So BFS can also be used to find minimum spanning tree of a connected, undirected or a weighted graph. By exploring the graph in a BFS manner and considering edges with minimum weight, we can construct a minimum spanning tree as well. So finding all the possible paths. So there is another Floyd-Warshall algorithm that does that. So it will be all pair shortest path algorithm is Floyd-Warshall. But you can also do that with this. Again, it will not be specifically used for that purpose because already there is an expert algorithm that does that. But BFS can also be used to find all the possible path between two vertices in a graph. By modifying the traversal slightly, BFS can be enhanced to store and enumerate all paths instead of just starting the shortest path. Okay, so just discuss the difference between the depth first search and the breadth first search. Okay, so first is the traversal order. So DFS explores the graph in depth first search manner, going as deep as possible, whereas the BFS explores the graph in a breadth first manner, visiting all the neighboring nodes which are placed at the same level. So keep that in mind. Okay, so if you have a different graph which is longer in depth, so the depth first search will be exploring. Suppose this is a graph, something like this, that is going deep. So depth first search will be like this, yeah, this, okay. But the breadth first search will explore give priority to those nodes which are at the same level. Okay, keep that in mind. Another is the data structure. We have already discussed that data structure that is being used in depth first search is stack, and in the depth first search is Q data structure. Path determination, so DFS may not find always the shortest path, but breadth first search guarantees finding the shortest path. So this is one difference between them. DFS has lower memory requirement as it explores a single branch at a time. BFS requires more memory because it explores all branches at each level. Implementation complexity, if you see, DFS is relatively simple to implement and BFS is a little more complex to implement, and the applications of it is maze solving, cycle detection, topological sorting and graph coloring, and the applications of BFS is shortest path finding, web crawling, social networking analysis and puzzle solving, and etc. There are many other applications. So all in all, in this particular session we have seen the working of the breadth first search algorithm, how the breadth first search algorithm is different from the depth first search algorithm, how the data structure impacts in the searching part, and we have also discussed some examples, and we have also seen the applications of depth first search and breadth first search. So thank you.